Hello and welcome back. Today we're going to derive the electric field from a dipole. So a dipole is a pair of charges, one positive and one negative. And these charges are separated by a fixed distance we're going to call L. Okay? And we're going to define our coordinate system. So we have the z direction pointing upwards. So if we take the origin at the centre of our dipole, then we're going to have a vector to the positive charge, which is going to be L over 2, and to the negative charge we have a vector minus L over 2. Okay, since we know that L is defined in the positive z direction. So we want to find the electric field at an arbitrary point away from this dipole. So we can draw a vector R to a point P. Okay, so let's find the distance from each charge to this point P, and that's simply basic vector subtraction. So the distance is going to be the modulus of R subtract L over 2. And for the negative charge, like so, since this is minus L over 2, then this distance is going to be R plus L over 2. Now this is going to be in spherical coordinates, so we're going to call this angle theta. This is the angle between R and the z-axis. And of course we have our radial unit vector, which is psi hat. Okay, so this is in Cartesian coordinates, z, so we can write this in terms of our spherical coordinates. This is going to be L, but the z unit vector is written as cos theta r hat plus sine theta psi hat. Okay. So using Coulomb's law, we can find the total electric field at P by summing the electric fields from each charge. So E defined at P is going to equal Q over 4 pi epsilon naught, and then for our positive charge we're going to have R minus L over 2 divided by the magnitude of that distance cubed minus Q over 4 pi epsilon naught, and then for the negative charge R plus L over 2 divided by that modulus cubed. Okay, so we have positive and minuses here. We can take those and say we have R plus or minus L over 2. Okay, using our definition for z hat in terms of our r hat and psi hat, we're going to get, this is going to be the same as R plus minus a half L cos theta r hat, and then plus or minus a half L sine theta psi hat. Okay, simply using our definition here. So in order to have an expression for EP that is easy to calculate with, but we seek an approximate expression. So we're going to make the assumption of an ideal electric dipole. An ideal electric dipole is one in which the electric field for L over R is much less than 1. Okay? So it means this distance is considerably smaller than the distance we are with P. So this point is very far away. So taking this, we can have a more explicit form R plus or minus L over 2 is going to equal the square root of these components. So we're going to have R plus or minus a half L cos theta squared plus a quarter L squared sine squared theta. Okay. So from that, we get cos squareds and sine squareds will cancel out to give us r squared plus or minus LR cos theta plus 1/4 L squared. Okay. Taking out R, we have R square root of 1 plus or minus L over R cos theta plus 1/4 L over R squared. Okay, so we can approximate this as R into the square root of 1 plus or minus L over R cos theta. Okay, because we're simply ignoring the second order terms because we know this is considerably less than 1 as we're dealing with an ideal dipole. Now if we use our Taylor expansion, 1 plus epsilon squared is going to approximately equal 1 plus n epsilon, okay, for epsilon is much less than 1, which in this case it is. So this expression becomes approximately equal to R into 1 plus or minus L over 2R cos theta. Fantastic, okay. Now, as we're dealing with Coulomb's law, we should really focus on the reciprocal of our magnitude and get that in a easy to deal with form. So L over 2 cubed. That will therefore, from this, approximately equal to 1 over R cubed into 1 minus plus 3L over 2R cos theta. Okay? So, from our electric field, we get E defined at P is equal, or approximately equal. If we pull out a Q over 4 pi epsilon naught, okay, we have our first charge, R minus a half L cos theta, defined at R, minus a half L sine theta psi, in brackets, okay, multiply this by our reciprocal of the magnitude cubed, so it's going to be times by 1 plus 3L 2R cos theta. Okay, so we're going to now minus for the negative charge r plus L over 2 cos theta r hat direction plus half L sine theta psi direction multiplied by 1 minus 3L over 2R cos theta. Right. So leaving that up there. So if we neglect the second order terms when we do these expansions, you can try out the expansion for yourself, but neglecting second order terms, we can say EP is approximately equal to Q over 4 pi epsilon naught R cubed, okay, into 2L cos theta R hat minus L sine theta psi hat. Okay. Now, a little trick. We're going to do a backward step, but you'll understand why in a minute. That's going to be 3L cos theta R hat minus L cos theta R hat, then minus that L sine theta psi hat. Okay, but you remember that our definition of the z unit vector, okay, was cos theta R hat plus sine theta psi hat, right? So using this, and also the fact that we know cos theta, okay, from our diagram it's simply going to be the dot product between z and r, because it's the angle between z and r vector, the z unit vector. So knowing these, we can then approximate this as q over 4 pi epsilon naught r cubed into 3L z dotted with r unit vector minus L z hat. Now finally, using the definition for an electrical dipole moment, the electrical dipole moment P is going to equal the charge times the distance between the charges, which is L z hat. Okay, so we therefore get that our electric field from the dipole at any point is approximately equal to 1 over 4 pi epsilon naught r cubed into 3 p dotted with r unit vector times r unit vector minus p. And that's our electric field from our dipole.